Hey guys, so in this video we will be talking about Bohr's model of the hydrogen atom. And so the first thing, before we do this, and even before we explain Bohr's model, is I want to just note that I have some equations. I've got 8 equations up here that we will be using in this video. And so hopefully all but probably this one you may be familiar with, but I will explain them in a minute. Just wanted to let you know why that's there. And then over here, I've got a picture of Bohr's model. And so for Bohr's model, right, we've got a proton in the center, and we have an electron going around the proton in an orbit. It's also called the planetary model because it's an orbit like the planets around the proton at a radius r away. And the electron is, it could be going in either direction. That's not really important for the math of this model. Now, this model is based off of the experiments that we talked about a few videos ago, as well as the spectral lines that we also talked about a few videos ago. And this model will actually explain both of them. The first thing I have to note here is that this model is wrong. We will find and develop through quantum mechanics that this model is incorrect. So why do all the calculations for it? Because it turns out that the equation that this model predicts for the energy level is actually correct. And we will rederive that equation using quantum mechanics at the end of section 6, which is pretty incredible. Because the physics that we're going to be using to get this is inapplicable. We're going to be using classical mechanics, and classical mechanics cannot describe the motion of an electron in an atom. And as I think we've probably mentioned before, there's really a probability cloud. The electron is not in a fixed orbit. So the fundamental assumption when we're doing this calculation is just purely wrong. Yet it gives us a correct result. And that's pretty impressive. And so that's why we're going to be going through this and looking at it and why this was accepted until Schrodinger's model. In a way, there are definitely some problems with this model that I may touch at around the end of this video. But in general, this model was at least had something to it because it was getting the correct results that matched the experiments. Okay, so now I want to touch on these equations here. So the first thing we have is P equals mv. This is momentum, particularly the magnitude of momentum. I don't have the vector arrows on there. And then in a few places I've explicitly shown that these are magnitudes. So, for example, angular momentum, when you're going in a circle, and I believe I talked about this in a video in section 0, angular momentum for a circle is the magnitude is the radius times the magnitude of the momentum. This is only if you're going in a circle, but that's what we have in this model, so that's what we'll be using. The next thing is an assumption that Bohr made about angular momentum. And he actually made this assumption. It was prompted because of the spectral line experiment, that we know that the energy levels of the electrons in an atom, because this is also after Rutherford discovered the nucleus and the electrons around the nucleus. The energy levels of those electrons, with them catching light and releasing the light, right, which showed the difference in the energy levels, that when you look at that, it's quantized, it's discrete. And so one of the ways Bohr figured out how to get that is he said, well, assume the angular momentum is discrete. And this is something that he figured out if he did this, he would get discrete energy levels, and it turned out these were actually correct discrete energy levels. Okay, so then we have some energy equations. We know energy is T plus Vt being kinetic energy, V being potential energy. T is P squared over 2m. If you use this top equation, P equals mv, and then this P squared over 2m, you'll find that that's 1/2 mv squared, which we know is another way of writing kinetic energy. Potential energy, when you have two charges, hopefully you'd be familiar with this if you're familiar with a little bit of electricity. I believe I did mention these equations in my video on electricity. V, the potential energy, between two charges is K, Coulomb's constant, which is 9 times 10 to the ninth Newton meters squared per Coulomb squared, approximately. So that's it's just a constant. Then the product of the two charges, Q1 and Q2, over the distance are between them. And then we know the relationship between potential energy and force. And given this, you can find that these are correct, because if you use the equation, if you just take the derivative with respect to the radius of this of the potential energy, right? F is negative dV by dr. Then you will end up getting this correct expression here. Okay. And so this is the force between those two charges, and then the potential energy with the interaction. And then we have the net centripetal force is mv squared over r. And there's one more thing that I do want to add here, is there is a negative sign here. And this is just because of how we define positive and negative directions, at least when we're talking about electricity. So positive directions for a force means the force is outwards, which would make sense. If both charges are positive or both charges are negative, there would be an outwards force, repulsion, right? And this force would be positive. One's positive, one's negative, the force would be inwards, which is attractive, which it should be, because we have a positively charged object and a negatively charged object. And then the centripetal force, this is the force that keeps an electron, or keeps, not just an electron, keeps anything going in a circle. You actually need to have a force, and hopefully you'd be familiar with that. That's definitely something really covered in introductory physics class. But the equation for the net centripetal force, all the forces on an object, in order to keep it in a circle, must equal mv squared over r. And I have the negative sign because it's pointed inwards. Okay, so we're going to be using these equations to derive the energy levels in Bohr's model. And remember, the fundamental assumption that we're going to be making here, besides, this planetary orbital motion, is that angular momentum is quantized. Okay, so let's start with our idea that the centripetal force, and I'll keep doing this. I'll do this, and I'll start here in red. So we know that the net centripetal force is going to be minus mv squared over r. But we have to think about, well, what is the force? And we're analyzing the forces on the electron. What force is keeping it in an orbit? Well, that would be the electric force, right? So we can set these two equal to each other. So k q1 q2 over r squared, right? This has to then be equal to k q1 q2 over r squared. But we know q1 and q2, it doesn't matter which one is which, but one's the charge of the proton, one's the charge of the electron. Proton is positive e being the elementary charge unit, and 1 E is approximately 1.6 times 10 to the negative 19th coulombs, but we'll just use the letter E for right now until we plug in some numbers at the end. And then the other is negative E. So if I have E times negative E, that's negative E squared. So minus mv squared over r equals negative, right? Negative E squared, so we can bring the negative out front, negative k E squared over r squared. Okay, perfect. So we can cross out the negatives, which makes sense, right? Both the net centripetal force is inwards, the electric force is inwards. Okay, so now we can show, using this, we can show that we have, if we want to multiply through by r squared, we get mv squared r equals k e squared over r squared. Oh, sorry, no, we're not. Sorry, we're multiplying through by r squared, so we just get k e squared. And so now, the next step in our algebra is going to be multiplying by mv over mv. or sorry, mr over mr, which is a perfectly legal step. We're just multiplying by 1. We just multiply the numerator and then the denominator by the same amount. And you will see in a second why we might be doing this. So I'm actually going to flip the order here so to match what I have in my notes here. So we've got ke squared equals m squared v squared r squared over mr. And looking here, right here we have, so m squared v squared r squared. If we look at this, that looks like angular momentum squared, correct? Because angular momentum is mvr. Angular momentum is mvr because momentum is mv and then times r. So this would be ke squared equals L squared, and that's the magnitude of L, but L squared, it's just the square. So L squared over mr. And now, the next thing that I would like to do is solve for r. Okay, so this should not be too difficult. I can just bring this up here. If we solve for r, we have r equals L squared over mke squared. And L now we can use our assumption about Bohr's model where the angular momentum is quantized. So L squared would be h bar squared n squared. So R equals h bar squared n squared over mk e squared. And now the only other thing that we need to do here is we know the mass of an electron, right? By experiment we have found the mass of the electron, and so we call that little me, and the mass of the electron, I believe, is 9.11 times 10 to the negative 31st kilograms. So a very, very small mass, if we're converting into kilograms, just so we can plug everything in here. Now, notice what we have here. We have, this is equal to, so R is h bar squared over me k e squared times n squared. Well, notice h bar squared is a constant. Me k e squared, these are all either constants or observable quantities, things that we have observed. We know the value of me, we know the value of e squared. So this is all things we know the value of. And in fact, if we plug in the numbers here, well, actually, the first thing is I just want to give this term a label here. So let's call this thing right here. Going to call that R1. Actually, R1, or sometimes what I think I would actually like to call it is A. And some people will call it both things, but so we'll call it A. I think that's just, for me at least, the way I learned it, seemed more standard. So for A is equal to this h bar squared over me k e squared, and we can plug in numbers here and find the value of this is 5.30 times 10 to the negative 11th meters. So this is about 1 billionth of a 5.3 billionths of a centimeter, which is very, very, very small. But this is, it appears, the radius, at least for the first energy level, for n equals 1. When n equals 1, this is the radius, and that's why some people will call it R1. Okay, so this is, and then we call it the Bohr radius. So we have found, and just to summarize our results that I'll write here, the radius, because it turns out the radii, how far it is away from the proton, is quantized according to Bohr's model, where R is equal to A times n squared, where A, and I'll do this in green here, where A is 5.3. This is a Bohr radius times 10 to the negative 11th meters. Okay, so that is the first thing that we found, that the radii are quantized in Bohr's model. So now that we found the radii, let's see if we can go ahead and look at the energies, which will be our next task here. So I'm going to erase this. Hopefully you have this all written down if you would like to have it written down. This is definitely an important derivation to know, just in terms of how physics has developed over time. Okay, so we can start with our equation for energy, right? What we know energy is T plus V. And we can use some quantities here, our T and V here to substitute in. So E equals T plus V. But we know T is P squared over 2M. So let's write that here. We got T is P squared over 2M. And then plus K Q1 Q2 over R squared. Oh, sorry, not R squared. That's just R for potential energy. Okay, so now we've got to look at what this P squared over 2M is. So let's go back for a second to the proof that we had before, right? Where we were doing our where we were doing the proof to find R, or the derivation to find R. And one of the things we found was this expression. We found that Ke squared, I'm gonna go back here, Ke squared equals M squared V squared R squared V squared R squared over MR. Okay, so now given this, we can write this. We want to find, really what we're looking for is the value of P squared over 2M. Okay, that's what we're looking for here, and this is a bit of a tricky step here, but we have M squared V squared R. Well, M squared V squared is P squared, and then the R squared and the R can cancel. So let's say we have Ke squared equals P squared R, because that over M. Okay, we are almost done. Now we can show that P squared over 2M equals Ke squared over 2R. All we have to do is divide by 2R. Divide both sides by 2R. We get P squared over 2M equals Ke squared over 2R. So that apparently is our expression. We just have to go back to that previous to the previous derivation to find our expression for P squared over 2M. So now that we have done that, we can rewrite that here. So P squared over 2M is Ke squared over 2R. Now K Q1 Q2 over R, well, again, Q1 Q2 is minus E squared, so this would be negative Ke squared over R. Okay, and I'm just going to make a note that we took this from here, put it there. Okay. So now we can factor out this Ke squared over R, and we get, so this is Ke squared over R, and this is all the energy, so I'll write that here. Ke squared over R times, if we factor that out, we get 1/2 minus 1. or 1 half minus 1, negative 1 half. So putting this back in, E equals negative Ke squared over 2r. And that is our expression for energy. But now we know that r is an squared. So let's plug that in here. E equals negative Ke squared over 2an squared. Okay, and now we'll write this like this. This is negative Ke squared over 2a, then times 1 over n squared. So, just like we did before, now we have this constant term out front. This is a constant. And so we can actually plug in and find the value for it. So if we plug in and find the value for this, and I'm going to call this term, I'm going to call it E1, is, let's see, this is negative 2.18 times 10 to the negative 18th joules. Okay, and then we know now that the energy, and I'll write this over here in red here, the energy of an electron in the Bohr model is negative 2.18 times 10 to the negative 18th joules over n squared. And so this is, and then you can call it E1, negative 2.18 times 10 to the negative 18th, although usually how I see this written, it's usually written just like this. The only constant we usually give a really special name for is this A constant. Okay, so now looking at this, we know that the energies, we're calling them negative, but the reason that's okay here, I mean, again, energy is relative, as I think we've mentioned before. It depends on where you define potential energy equal to 0 as. But if you are to sort of, not really graph, but sort of make a diagram of these energies, which we will have, actually I have this set up for the next video where we'll talk more about this, but I'm going to go here. And so just so you know, this negative 2.18 times 10 to the negative 18th joules is approximately negative 13.6 electron volts. And these are the energy levels. So down here we have our lowest energy level, right? And then for our next energy level, n is 2, so we have to divide this thing by 4, which takes us here. And then we have to divide this thing by 9 to get here, right? So we take this, our lowest energy, our negative 13.6 electron volts, or negative 2.18 times 10 to the negative 18th, and then divide it by n squared. So then we get our third energy level is negative 1.51 electron volts, which is obviously bigger, right, because it's less negative. So the energies do go up. And at infinity, they asymptote out here to 0. So the highest energy level, there's no highest. You can go as high as you would like, but you will, flatten out at 0, and the energy levels get closer and closer and closer together as you get closer to n equals infinity. And then we'll talk more about what the Lyman, Balmer, and Paschen series are in the next video. So this was the Bohr's model. And this result, this energy result, is incredible because really we get the same result when we apply the Schrödinger equation, just we actually are using correct physics when we use it to get the Schrödinger equation, or when we get it through the Schrödinger equation. But hopefully this derivation made sense, and we'll talk more in the next video about how this actually matches up with our experimental results for the spectra from the energy spectrum of hydrogen.